Hello class, welcome to the final segment of Lecture 10, and we will go ahead and wrap up Lecture 10 by going through an exercise to sort of check your understanding on the equations we derived in the natural coordinate system and how to actually apply them, and how to calculate some of the various quantities that we also looked at. So, just like with the other exercises, I'll just go ahead and read the problem out to you. So, calculate the magnitude of the pressure gradient force, the Coriolis force, and the centrifugal force for a half-mile wide tornado with a wind speed of 55 meters per second and a minimum pressure of 970 millibars located at the center of the tornado. Assume the pressure at the outer edge of the tornado is 1,000 millibars, the tornado is at a latitude of 40 degrees north, and the density of the air is 1 kilogram per cubic meter. So with that, I will go ahead and ask you to pause the video, take about 10-15 minutes, try to arrive at some solution to the exercise in question. And once you feel comfortable with your solution, unpause the video, and hopefully the solution you arrive at will look similar to what's on the screen here. So I'll give you a few seconds to pause the video. All right, hopefully the solution that you arrived at will look something like what you're about to see. So with that, let's go ahead and take a look at the solution. So first thing that you want to do is, and this is especially helpful for this particular problem, is to Diode diagram. So here I have a nice circle representing, basically representing our tornado. And if our tornado is in the northern hemisphere, then we'll assume that it's rotating in the counterclockwise direction. So we'll assume it's rotating something like this. And since our tornado is half a mile wide, that means the diameter of the tornado is going to be half a mile, and that therefore means that the radius of the tornado, which is going to be kind of important to keep in mind, the radius of the tornado is going to be represented as being a quarter mile. So, armed with that information, we are now in a position to actually start calculating the forces. So let's start with the centrifugal force. So the magnitude, and since we're only interested in the magnitude of these forces, we're not going to worry about negative signs. So since all we're concerned about is the magnitude, we're going to disregard negative signs entirely and just take a look at the magnitudes of the forces. So if we calculate the magnitude of the centrifugal force, that's just the rotational velocity, 55 meters per second squared, divided by a radius of a quarter mile, which if you worked at the unit conversions, that's roughly 400 meters. So the centrifugal force is 7.514 newtons per kilogram or meters per second squared. So that's a lot of centrifugal force for a tornado. 55 meters per second is all. By the way, 55 meters per second is roughly an EF2 tornado. So strong tornado, definitely not lower end, but not really high end either. Now let's take a look at Coriolis force. So the magnitude of the Coriolis force is just the Coriolis parameter times the velocity. So that's going to be 2 omega velocity times the sine of our latitude, which if we plug all those numbers in, we get 2 times 55 meters per second times omega, which is 2 pi over 1 Earth day, times the sine of 40 degrees, since we're in the northern hemisphere. And we get 5.137 times 10 to the minus third newtons per kilogram. That's the Coriolis force acting on the tornado. And last but certainly not least, pressure gradient force. And here we're going to use we're not going to use the isobaric form of the equation. We're going to use the standard pressure gradient force equation that we worked with before introducing the idea of being on a constant pressure surface. But if you do that, you'll get, and this is an instance where signage can actually be kind of confusing. So if you're rotating counterclockwise, it means your in-hat points toward the center of the tornado, which means as you're going in the positive in-hat direction, this would actually be positive 402 meters at the center of the tornado. So here at the brim of the tornado, your coordinate in the in-hat direction is 0, where your pressure is 1,000 millibars. So 1,000 millibars at 0 meters. And then at the center of it, that's where you have 400. That's where it's 402 meters in the direction of in-hat, where the pressure is 970 millibars. So order here is kind of important, just something to keep in mind as you're working in the natural coordinate system. So think about, when you look at the in-hat direction, think about, am I going towards higher values of in-hat or negative values of in-hat? And if you keep all that sorted out, then you should be able to avoid any sign errors. And since my pressure gradient points in the negative in-hat or in the positive in-hat direction, that means the pressure gradient force, since the pressure gradient points in the negative in-hat direction, it means the pressure gradient force points in the positive in-hat direction. So it points toward the center of the tornado. Just a sign convention that I want to go ahead and introduce and make sure that, just sort of make sure that there is not as much confusion going forward. But if we go ahead and work out all this in our calculator, plug in a value, we do in fact get a pressure gradient force as 7.452 newtons per kilogram or meters per second squared. Look how small the Coriolis force is in comparison to the centrifugal and pressure gradient forces. This is 3 orders of magnitude smaller than the other two forces. And this sort of emphasizes the point that we've made several times before, how Coriolis force is only significant on large scales of time and space. Tornado, very low end on the scale of space. This was a half-mile wide tornado, so not the largest tornado, but definitely not a small tornado either. But this is just sort of, this exercise was also meant to sort of illustrate how sometimes cyclostrophic balance is valid, because this Coriolis force is minuscule compared to these other two forces. So this makes sense to use cyclostrophic balance in the case of a tornado, just based on the fact that the Coriolis force is going to be basically unnoticeable. The tornado is not going to experience a Coriolis force. And this also explains how you can get an anticyclonic tornado, which is a tornado that rotates in the clockwise direction in the northern hemisphere. And that's just because Coriolis force really doesn't affect the tornado at all. So the tornado, it's not that hard for the tornado to rotate in the opposite direction, because it's not really fighting a Coriolis force. Technically it is, but it's so small that it doesn't care. But that was just another goal of this exercise, was just to illustrate how cyclostrophic balance can be valid, because in the case of this tornado, the Coriolis force, we can just disregard that because it's just so small compared to the other two forces. But as far as the actual exercise itself goes, hopefully you got some numbers that closely resemble those. If so, great. If not, make sure you understand the solution process. So that's going to do it for lecture 10, and again, cyclostrophic balance. And in the next lecture, we will take a closer look at the gradient wind balance and see what sort of role that plays in the atmospheric flow patterns in natural coordinates. So with that, I will see you all in the next lecture.